Hello and welcome to Enough with the Science, Season 2.
Yes, indeed. We're back after a summer of freedom and frolicking.
Yes, I'm Joe.
And I'm Senan. And this week we're going to start off Season 2 with a conundrum that has been keeping Joe awake at night.
Well, now, before we go into that, just to let you know that if you're new to the podcast and missed
Are you going to
one,
waste a minute of every podcast by telling
explain
people
it.
why we're here?
Yeah, absolutely. This is somebody's first time. They're switching on to us for the first time and they're going, what is this about? Why would I listen to this for the next
Okay, let me short
25
circuit
minutes?
this, right? This podcast is Nerd versus Joker.
It's it's like it's like a Marvel comic that's gone wrong on air. And so basically, Senan is the nerd and I try and derail his nerdness.
So what is it that's been keeping you awake at night, Joe?
Well, basically, it's a simple question. I can't understand, right, there's two ideas in my head that I just can't mesh together. Now, this happens to me many times, but I don't often have the opportunity to let Senan enlighten me and let me get some sleep. So, okay, the two ideas are the law of conservation of energy, so that energy cannot be created or destroyed. It can only be converted from one form into another.
Yep.
Versus the slow, inexorable death of the universe, where eventually everything just blinks out and everything is cold and dark and there's nothing left.
So you mean some kind of generic death, or is there a specific kind of death of the universe you have in mind?
Eventually, it just slowly, the last final star winks out.
So might the term heat death apply to what you're trying to convey?
I wish I'd used that as a band name at some stage. But I had never heard it until you brought it up. So, but
Okay.
maybe that is the official term for what I'm describing.
I think there is a theory, that the universe will eventually. Now we're talking about, it's estimated trillions upon trillions of years from now that the universe will eventually undergo something called heat death. Implicit, I think, in your question is the idea that in order for that to happen, all the energy in the universe has to somehow disappear.
Well, yeah, if you look at energy, like it's heat, it's light, you can see it, you can feel it,
Yeah.
it does stuff.
Yeah.
And then if there's nothing but a cold, dark, black, dead universe, and I hope you're not tuning in to be cheered up this week. But if that's all that's left, then where's the energy gone? Where, that's what keeps me up at night.
Okie doke. Right, I'm going to give you the answer first, and then we're going to delve into the details, right? So
Right. The answer is I have the wrong end of the stick completely.
The answer is that the energy which currently is ordered in a particular way, all of it will become disordered. So all of the energy will still exist, but it'll all be disordered.
Entropy. I love it.
Entropy is exactly what you're talking about. So another term for the maximum, for the heat death of the universe is maximum entropy.
Oh, maximum entropy.
Yes, yeah. So entropy just in this context just means disorder of energy.
Essentially, entropy means that in the way our universe is ordered at the minute, that it kind of goes from order to disorder. Energy moves from situation.
and that is the kernel of what's causing the heat, or will cause the heat death of the universe eventually. So, but we need to first of all talk about what the hell is energy anyway. Now, the fact is, energy is not a thing at all. It's not like everybody has been taught in school about conservation of energy and this kind of energy and that kind of energy. Energy as a thing, as one single thing, just doesn't exist. It's a nice little human invention. It's an abstract concept we've invented to describe lots of different things. And what they all have in common is that we can get some kind of work out of them. We can use these, piggyback on these phenomenon of loads of different kinds, and we can get some kind of work out of them.
Some kind of work out of them?
The potential to do work for us.
Okay.
That's essentially, so any process in the natural world, by that I mean the universe, not just the natural world on Earth, that has the potential to do work for us is essentially energy, as far as we're concerned. And
it's kind of selfish way of looking at energy. You have to work for us. Yeah. If you don't work for us, you're not energy.
And that's yet another definition of the heat death of the universe is when the universe's ability to do any work expires. That's the heat death of the universe.
Okay. I think you're going to maybe have to define work.
Yeah.
What's work?
Yeah, we'll come to that, right? I want to talk about the disordered part first. So another way of describing it is disordered energy. In other words, when the entire universe is just composed of disordered energy, that's also the heat death. What do I mean by disordered, right? So I'm going to give you a little analogy, which is probably going to break down pretty quickly with one or two questions from you. But
here we go. I'm ready.
Let's dive in. I want you to imagine you've got a little jam jar, right? And it's empty. You've washed all the dregs of the jam out of it. And you've 3 small piles that are not touching each other in the bottom of the jam jar. One of them is sugar, one is salt, and one is pepper, right? 3 little discrete little piles. You put the lid on the jam jar and you shake the hell out of it, and then you put it back down on the table. And what you had was 3 piles of ordered energy, and what you now have is one big pile of disordered energy. You can't, the work of making your food sweet, you can't use it for that purpose, because if you put a spoonful in, you're also going to get salt and pepper taste, and vice versa for salt or for pepper. So that's an analogy of the difference between ordered and disordered energy, in that, you no longer can get useful work out of that.
Okay. Just to be really mean, right?
Yeah.
So disordered energy, we can't get any work out of.
Yeah.
So then it's not energy.
No, it's energy in that it is capable of creating activity on the microscopic level, but the activity is so random and so multi-directional that there's no coherent direction to it. So, say the flow of a river, right?
Yeah.
So the water in a river, it's all flowing in one direction. So that has a coherent energy flow in it. It's kinetic energy, the movement of the water, and we can make use of that with a generator that we put or a water wheel or whatever into the river. So that's a coherent energy. It's all flowing in one direction, and we're basically going to piggyback on that flow to generate electricity, for example.
Okay. So the light of the sun.
The light of the sun is energy that is coming down that we can make use of. So I want to draw you. So that's orderly energy, like the flow of the river. Now let's talk about disordered energy. I gave you one analogy there, the jam jar, a minute ago. Another one is a room which is completely sealed. Imagine a room with no doors. Why would somebody build that? Anyway, let's assume that there is a room which is completely sealed, and the air in the room is all at the same temperature, and the walls of the room are at the same temperature. Okay, so there's no energy flow going on anywhere there. So it's not, you don't have a situation where one side of the room is hot and the other side is cold, and the heat is trying to flow across to make up the difference. That energy, so there's still plenty of energy in that room, in that if you look at the molecules of air down at the microscopic level, they're all bouncing around like molecules always do, but they're doing it all in random directions. There's no coherent direction to the force being exerted by those molecules. Has anybody
built this room? Has anybody ever done this as an experiment? Try to build this Schrodinger's air.
Well, if there was a cat in there, there would be, of course, some energy.
He should have worked with other things. He could have done Schrodinger's elephant.
Well, I suppose it's just easier to pick up the cat, isn't it?
And nobody cares about cats. Oh, that's it. We're cancelled. Cancelled already. First episode of the second season.
So that's the room is kind of a bit of an analogy for the universe when it undergoes heat death, in that all these molecules are still there with their own little discrete packet of energy, but they're all moving around in different directions, and it evens out to be one homogeneous mass that has no particular coherence. It's all disordered.
Okay, so energy has to be coherent to be energy. If it's not coherent, then it's not.
Well, to be energy that we want to make use of, yes, yeah. That's a very interesting idea, coherent. We mentioned the river, of course, that's one example. Another example is a boulder hanging out of a crane. So boulder is 20 feet up in the air and it's suspended from a rope that's connected to a crane. Obviously, it's not moving, but it has a lot of potential energy just by sitting there. And all that potential energy is focused towards the ground, towards the earth underneath it, because gravity from the earth is pulling against it. So again, even though it's not moving, it has this coherent potential energy focused towards the ground.
To land on, for example, a cat.
Potentially. It might make a cat burger if it hits just right. So we've touched on this idea of energy is only something we're interested in calling energy if we can get some work out of it in some shape or form. And then we've got to talk about energy gradients. So that's a bit of a complex, abstract topic.
I'm going to come back in about half an hour. Will you just talk away?
So tell me, actually, before we go any further, what's your concept of a gradient?
A gradient is like up a hill. There's a hill. There's a gradient when you're trying to go up a hill in the car in the ice, and there's a gradient up the hill. And depending on the gradient of the hill and how good your tires are, that will dictate how long it will take you to get up the hill. So there's a difference between the bottom of the hill and the top of the hill, and there's a kind of connection between them.
Yeah. So would you say it's like the angle of the slope?
Well, maybe that's the definition. Yes, yeah. I wouldn't disagree with that, Your Honor. I'm just going to consult with my client.
So imagine a ball sitting on top of that hill, and there's like a bit of a rock holding it, stopping it from roll down the hill. There's an energy
We're very
gradient.
boulder-centric today. We're having a very boulder rock-centric
Rock,
podcast.
paper, scissors.
Okay, so the ball is there.
So the ball's there, but it can't roll away because something's in the way. Okay, but it's on top of the hill. So that there's an energy gradient there. It just is a coincidence that the hill also happens to have a gradient called a slope. But essentially, that ball is like the boulder swinging out of the crane. It's got potential energy to go down the hill. But anyway, let's try and define what I'm talking about as an energy gradient, because it's a key part of this concept of something we can, a difference we can exploit to get work out of it. So essentially, if we think of a situation where we have two bunches of stuff, we're getting into the real technical language now.
Okay, two bunches of stuff.
And those two bunches of stuff might be side by side, or if they're not, they're somehow connected with each other. Okay, but we'll look at the side by side example first. If you've got a balloon, you blow it up, and then you hold the nozzle, which are block it with your fingers. So inside that balloon, you've got a load of high pressure air that you blew into it. And then around the outside of the balloon, in the atmosphere around us, you have air, but it's at a much lower pressure. So there's a gradient there. There's a difference between the high pressure in the balloon and the low pressure outside, okay? And as soon as currently you have blocked the pathway that would allow one gradient, the higher pressure part to flow into the lower pressure part, because the gradient wants to equalize itself. The gradient wants to naturally go away.
Okay, so the nature of gradients are to disappear.
Are to gradually, some fast, some slow, to disappear.
Yeah.
So let's say you take a little propeller thing and you attach it to the nozzle of the balloon, and then you release the nozzle of the balloon. All the high pressure air will flow out to equalize with the low pressure air outside, and along the way it'll spin that little propeller and maybe generate a piece of electricity for you. So that's essentially what a gradient is. We used high pressure as an example, but we could have used other ones, say chemical energy, like a battery. So in a battery, you've got on one side of the battery, you've got a load of free electrons, and on the other side, you've got a load of positively charged protons. So that's the negative and the positive terminal. Normally, they're not connected to each other, but you introduce an electric circuit, or maybe you connect a torch to the battery or your mobile phone or something, and now they can flow. So although the two bunches of stuff, that is the negative part of the battery and the positive part, are not actually beside each other in the same way that the air in the balloon was, as soon as you make a circuit from the positive side, you're making a connection between those two areas, and that's allowing the flow. The gradient wants to even itself out, i.e. flatten the battery.
So gradient, you could use like just a difference in
a
concentration.
A difference that wants to resolve itself, a difference that wants to flow so that the difference goes away.
Yeah. So like essentially there's either more of one in one place and less of one in another place.
Yeah.
And the stuff wants to go to where less is.
Yes, essentially, yeah. And we piggyback on that in various ways to get work out of it.
Okay.
I mean, even did I mention this already? The engine of a car, you've got a little explosion takes place inside in the cylinder, and suddenly you've got the explosion produces a pile of high pressure gas. But outside the cylinder, the gas is at a much lower pressure, so it pushes the high pressure gas inside, pushes the piston down in its attempt to get back out to get rid of that gradient. It pushes the piston down, which turns the engine for us, and we get work out of it.
Yeah, you did say that already.
Yeah. Okay. Well, now
I don't know. I wasn't listening.
Now it's been doubly reinforced.
Okay, so gradient, essentially, there's a difference in.
Yeah.
I want to say concentration, but maybe that's not the right word. But it wants to flow from it. There's a lot of something over here, and there's not so much over here.
Yeah.
And it wants to equalize or.
Yeah. That's pretty much that's as good a description as you're going to get.
We're in trouble if that's as good. We are in real trouble as a science podcast.
So that's the universe is absolutely chock full of gradients. So every star, every sun, every black hole, all of the energetic stuff that's happening around those celestial bodies is all down to a gradient. Like there's a massive gradient between the heat and pressure in the middle of our sun and the surrounding space, which doesn't have anything like the same amount of heat or pressure. So that's why all this energy is streaming out of the sun. It's trying to resolve that gradient. It's trying to flatten that gradient. When all those gradients in the universe are gone, then
Okay. Here's the happy thought.
That's the
we
heat
should
death.
have some sad.
That's the heat death.
Sad music. Okay.
When all those gradients are gone.
So the energy isn't gone.
No.
Just the difference between the energy gradients.
Between the pockets of stuff.
Pockets of stuff is gone.
Is gone, yeah.
But the energy still, but it's not energy because we can't make it work.
It's not energy by our definition, but it's still energy at a nanoscale level, of molecular level. Those molecules are still vibrating the way they've always done, but now none of them are coherent. None of them are all going in the same direction.
But then is there not the possibility that it'll spark off again?
So there are some wild theories about the potential for the universe recycling itself.
Okay.
But they're wild and very, very speculative. But there is, at a local level, of course, we are able to reverse gradients. I mean, you can recharge the battery in your mobile phone every day. So that's an example of a gradient being reversed. In other words, you're recreating the gradient that gradually ran down during the day as your phone battery ran down to zero.
Right.
But you might then start to ask me, well, can't we just resolve all the gradients or reverse all the gradients in a similar way and stop the heat death of the universe from happening?
Yeah.
But you see,
but why would we want to do that? That's my question.
Well,
the way the world is going, heat death of the universe is the best we can hope for.
Maybe we want to accelerate it.
We're going to recycle the universe. No.
The thing about reversing a gradient is you have to use another gradient to do it.
Uh-huh.
So, the electricity that you use to recharge your phone battery is coming from a generator somewhere, which is piggybacking on another gradient to generate that electricity. So you're just shifting the gradients around.
So if you don't have any gradients, you can't fix the gradients once all the gradients are gone.
Yeah. Plus, there's another problem. All these processes that we use to piggyback on one gradient to get work out of it, they're all imperfect. In other words, we don't get all of the energy into a usable form. So say that generator that's generating the electricity is from a hydroelectric scheme. Some of the energy of that water that's flowing through the propeller is going to be lost to friction in the ball bearings that the propeller shaft is spinning on, to viscosity in the water, to various things like that. And so what's happening there is that a small amount of the energy is becoming disordered and useless to us at that point. And every time we make use of a gradient for some purpose to do some work, small amounts of the energy are not correctly converted to the work we want, and they end up being disordered energy that's of no use to us anymore.
Ever.
So ever, in all likelihood, ever. With the result that leakage, it's not, I don't like using the word leakage because it suggests that the energy is going away somewhere. It's not going away, it's just becoming disordered. But that leakage gradually accumulates over time. So even though we might, obviously we humans don't have the technology or the scope to reverse all the gradients in the universe. But let's say we were super aliens who could do that. It would only delay the heat death of the universe, because every time we reverse one of those gradients, we're actually losing a little bit of the energy. It's leaking away into a disordered state. And
just as far as the happy thought of the heat death of the universe goes, is that the sort of accepted, inevitable end of everything?
Well, it's probably the most accepted theory about how the universe will end. I mean, look, we're just smart monkeys. We don't understand everything, but it's
Speak for yourself.
But it's an interesting point you raise, because if you look at it philosophically, we are a component of the universe. So by us having this discussion and scientists having these thoughts, it's the universe contemplating its own demise.
Yes.
Which is a pretty amazing thing, that the universe has developed sufficient intelligence to be able to actually become aware of the prospect of its own demise and maybe look for ways to avoid it or delay it.
Yeah. Well, it just frightens me that we could be considered the intelligence of the universe. Surely it could do better.
Well, one or two of us anyway.
surely at this point it could do better. It's got trillions of years. It's like maybe it'll figure out. But I do think. I mean, the first thing that would occur to me is that the heat death of the universe is just it's all of this disordered energy.
Yeah.
If there was a way for it to reorder itself, like it's still there. I mean, it's not energy, whatever you want to call it. It's not doing any work. But I mean, all the molecules are kind of dancing around the place and kind of going, okay, I'm doing my own thing at the minute. But if it ever decided to kind of head.
So, maybe the infinite number of monkeys with the infinite number of typewriters who theoretically could come up with the works of Shakespeare if you give them enough time. I mean, maybe the random motion of the molecules in the universe would eventually line up.
Yeah. Maybe they're like they're all equally random.
Yeah.
But they're all equally random.
I think the monkeys are more likely to make Shakespeare than for that to happen. Leaving aside the fact that Shakespeare was, I suppose, an advanced monkey.
Well, that's all we can ever hope to be, advanced monkeys.
So now you think you've got a good understanding of it all.
No, I don't. I actually don't, because I still like, if I see a cold dead universe, like I suppose, of course, being human, we think we should be able to perceive energy. You should be able to see it. You should feel it. It's got to be light. It's got to be heat. It's got to be explosions. It's got to be stuff.
Yeah.
But like, at the end of the universe, when there's just nothing that, like, there's no noise, there's no, that background noise that you hear in all the space movies, that's not there. There's no, like, it's just silent blackness.
Yep.
In all directions forever.
Yep.
And yet, all of those little molecules are still sitting there going.
Yep.
Like,
what a waste.
Well, it's just, I mean, the kind of, is this what they went to school for? Is this like, we worked really hard to become these molecules? Well, it wouldn't be molecules even. It'd be subatomic stuff, I imagine, is it? Or would it actually be molecules?
Good question. I don't know whether the molecules would break down themselves, whether the entropy, when the maximum state of entropy is reached, does that mean the molecules no longer have the ability to hold themselves together? I don't know.
Yeah.
I don't know.
Yeah.
But yeah, it's an intriguing thought that maybe it would actually devolve into the subatomic building blocks of the universe, the quarks and gluons and all the rest of it.
And then there's so many of them in so much space, surely two of them would just pop together into a new universe.
Well, that's probably what the Big Bang was.
This has all happened before. Have we made this podcast before?
But anyway, I'm going to throw a major spanner in the works now.
Okay. Oh, God. I was just getting my head around it. Okay, come on.
There's another form of energy that doesn't behave like I've just described for the last 20 minutes.
Of course there is.
At least it's a form of energy that we think exists.
Aha.
We've never detected it. We can only infer that it exists, and it's what's called dark energy.
So we infer it from
the fact that the universe is expanding and its expansion is accelerating.
Okay.
So there's some invisible force that we can't detect, which is causing. We can see the far off stars and galaxies. We can see that they're getting further away from us all the time. And the rate at which they're getting further away from us is getting faster and faster all the time.
But this always blows my mind. So they're all moving away from the center of the universe? Or
From
they're
each
all
other,
moving away from us?
From each other also.
Yeah.
So all space is expanding. So for example, if leaving aside the fact that the moon is eventually going to depart from Earth's orbit, but let's assume it never did, right? It would still gradually get further away purely due to the expansion of space. In other words, the amount of space between us and the moon would get larger because the individual pieces of space are getting bigger.
But do we notice that? Can we measure that, or are we all are we getting bigger? Like am I 1.5 times the size I was 13.5 billion years ago? I mean, is everything getting bigger? Or is it just the distance between?
I tell you what, you're doing a good job with the skin regimen there, because the wrinkles don't look one bit like 1.5 million years ago.
So when I was born, was I like 2 inches tall, and now I'm like kind of 50 feet tall? I mean,
no,
what do we know?
It's not on relative. It's not on that scale.
It's not relative, but is it relative? Are we all relatively getting bigger?
Oh yeah, you mean are we all getting bigger at the same rate due to the expansion of the universe?
Yes.
Yes, we probably are. But it's such a slow rate on our scales, on the scale of a human being, or even on the scale of planet Earth. The expansion is so slow that we can't perceive it. But we can, when you look over vast distances to galaxies and stars that are very far away, then you can measure it because of the amount of space between us and them.
But it's not just that, like, there's all of these clumps of matter and energy, and like the space in between that clump of matter and energy and the next clump of matter and energy is getting bigger. The actual clump of matter and energy is also
Yes,
expanding.
the entire fabric, everything is getting bigger.
But like
It's a mystery. It's a mystery.
we could have,
Fire Wilcox.
but we could have no real idea whether it was just sort of expanding and contracting or do whatever it was.
Oh, yeah,
It could be bigger and smaller and elasticated.
That is yet another one of those way out theories that potentially a point will come where it'll all just reverse and start coming in again. But is it going to happen? Who knows?
Yeah.
But like you're going to have a situation where the amount of energy that's currently contained in say 1 cubic meter of space maybe a trillion years from now, that same amount of energy might now be contained in 2 cubic meters of space because of this expansion.
Right.
So the energy is effectively getting diluted a bit by that expansion. So if that energy in that cubic meter had a gradient of some kind, that gradient is going to be flattened a little bit by the expansion. It's not that the energy is lost, it's that the energy is diluted a bit and spread out over a wider area.
But if there was a gradient, right, between that cubic meter of energy and the cubic meter of energy that's next to it, when they both expand to 2 cubic meters, surely the gradient would be the same.
Probably not locally. In other words, in one point.
Okay. Yes. Because,
So if you were to measure it across the full width of the 2 cubic meters, maybe it would add up to the same as it was originally.
Yeah. Okay. So as a whole, it would be, but
Yeah.
in at each individual point, it wouldn't be because they've moved.
Yeah. So that is actually that effect, that expansion effect, is also helping to bring us towards the heat death of the universe a bit faster than we otherwise would. And the weird thing about dark energy, as best as we can calculate based on very advanced mathematics that I don't understand, is that it doesn't undergo the same entropy or dilution. In other words, the cubic meter of space now, the amount of dark energy that's in that now versus what will be still a cubic meter, not the 2 cubic meters in a trillion years' time, will still have the same. In other words, the dark energy part won't have been diluted in the same way that all the other energy is. It's really mind-bending stuff, and there is no. You're about to ask me how does that work? Nobody knows.
Okay,
It's just based on the mathematics. So they observe. The astronomers observe the movement of the celestial bodies and calculate the speed of acceleration of the expansion, and from that they can work out the forces involved with dark energy, and from that they can work out, is dark energy diluting gradually as the universe expands, and it's not.
So that means dark energy is replicating itself.
We don't know. We don't know what like we understand so little about the mechanism behind the expansion of the universe. I mean, dark energy itself is not something we've ever detected. We're only inferring that it probably exists.
Well, we're actually just making it up to
to solve a problem for us.
We've observed this. So let's say it's like what's that word they used to homunculus.
Homunculus.
Yeah, that little man in your brain that like kind of like people used to attribute to like kind of people's actions. Yes, there's somebody in your brain or in your body.
He's usually very quiet in my head, except after a night's drinking when he starts playing the drums.
Well, yeah, they can be annoying like that. They can be annoying.
But it might seem that this is a very depressing episode of Enough.
I don't know. Look, this is trillions and trillions of years. We're going to wipe ourselves out long before that.
I was just about to make that point. I mean, it's like a newborn baby worrying about the provision for his old age care.
Yeah.
I mean,
although every newborn baby right now should be thinking about that. Get a pension, sign in, get a pension right now. The way the world is going. Yeah. But
so here's one more little philosophical conundrum I can leave you with.
Well, no, just now in terms of the dark energy.
Yeah.
So we can't talk about gradients and we have no idea about.
We don't think it has any useful gradients. It seems to push equally in all directions, which sounds like it might be a useful gradient, but because everything is pushing equally in all directions, the net effect seems to be no gradient.
Right. Okay.
Yeah. So here's a question for you. We'll leave as our parting shot.
Okay. Is this cheery? Is this something like Christmassy?
If all work and activity effectively ceases with the heat death of the universe, does that mean time has stopped as well?
Oh.
Because there's a theory that the universe's tendency to go from a state of very little entropy towards maximum entropy is effectively what is the passing of time. That's
So the definition of time is that like you go from a state of order to disorder.
Yes.
And that flow is time.
Now that's not a standard definition that everybody recognizes, but it's a theory.
Yeah.
And it's an interesting question. So when entropy doesn't get any worse because it's gotten as bad as it can get, does that mean time is finished?
I would imagine that in the countless trillions of years until the heat death of the universe, like that really would become the definition of an academic question. I think the practical application of that question is like, I don't know if there's something which is zero but concentrated, maybe dark zero.
Well, it would be handy. Say you've got a deadline for a project or something, or an essay that you've got to deliver, and you're running out of time. If you could zip forward to the heat death of the universe, you'd have ultimate, unending time to finish your essay. And then
or no time. Time would be gone. There is no time. There'd be less time, surely, if we went to the fast forward to
is
the
no
end
the
of the
same
year.
as less? I don't know.
Is no time the same as lots of time? I don't know.
Okay, well, it's probably enough time anyway for enough of the science this week.
Okay, well, look, just have lots of fun before the heat death of the universe. That's like, I mean, our parting shot has to be that there's lots of things that you can do in the trillions and trillions and trillions of years before maximum entropy ensues.
Live your life. Have the
Yeah.
crack, as we say in this part of the world.
Absolutely. Listen to our first season of podcasts.
And whatever else you do, make sure you subscribe and like our podcast.
Oh, yeah, absolutely. Yeah. And hopefully we'll catch you next time. I'm Joe.
And I'm Senan. All the best now.
Take it easy.